So now let's think about both of these cases uh, for an oscillator, and let's think about what is happening with some different quantities here. Uh, so let us think about velocity first. So for a mass on a spring, there are a couple different places I want to consider. One is maximum displacement in one direction. So this is going to be the equilibrium position where the mass would just hang at rest on its own. I want to think about when we're at equilibrium, and then I want to think about when we're at our maximum displacement in the other direction. The corresponding things for a pendulum are that it's swung all the way in one direction, it's sitting at the vertical, and then it's swung all the way in the other direction. Right. Actually, let's consider force first, because that will be more useful, and we can extrapolate what is happening with velocity based on what is happening with force. So let's consider net force. Well, we know that the force is proportional to displacement from equilibrium. So the force is a maximum at maximum displacement, both positive and negative, maximum displacement in both directions. We know that's true here from kx. We know that's true here. As theta gets bigger, sine theta also gets bigger until you pass 90 degrees. So the force is maximum at maximum displacement, and it is a minimum. I'll say the net force is a minimum. Actually, the net force is equal to 0 at that equilibrium position, the middle position of the mass. And we can see that very clearly. If you plug in 0 for theta, then this whole thing is 0. If you plug in 0 for x, then the force is 0. So now let's think about velocity again. Well, what are these objects doing? They're bouncing up and down. Okay, so at this maximum displacement, the mass will come to rest for a split second. Same for the pendulum. The mass will come to rest for a split second. So the velocity is a minimum, actually it's equal to 0, at maximum displacement, both positive and negative. And you might guess by correlation that it's a maximum at minimum displacement at equilibrium. That's a little bit harder to think about, but we think about that the force is always restorative in simple harmonic motion. It pushes back toward the middle. So as long as we're up here, there's a downward force. As soon as we get below, there's an upward force. So there's a downward force. That means it's accelerating downward, accelerating downward. As soon as it gets right here, the force is 0. So, and then as soon as it goes past here, then the force goes back upward, which means it'll start slowing down. So it's speeding up, and then at equilibrium, it switches over, and as it moves below equilibrium, then it's slowing down until it comes to rest. So if it's speeding up and then starts slowing down, the point right where that changeover happens is, of course, where the velocity is going to be a maximum. It's the same thing for the pendulum. Acceleration. Of course, acceleration is directly dependent on force. So acceleration is also maximum at maximum displacement, minimum at equilibrium, or at 0 displacement. And then the last quantity I want to think about here is potential energy. So you may not recall, but our spring potential energy that we talked about earlier in the year is 1/2 kx squared, where x is the displacement from equilibrium. So spring potential energy is also a maximum at maximum displacement and is a minimum at equilibrium. And then, of course, the counter to that, the opposite of that, is kinetic energy. Kinetic energy is going to go right along with velocity, where it has a minimum at maximum displacement and a maximum at equilibrium. So that's what's going on with simple harmonic motion. And in fact, the energy kind of swaps back and forth. So both spring force is causing the restorative force for the mass spring system. Gravitational force is causing the restorative force for a pendulum, which means that both of those forces are conservative forces, which means that mechanical energy is conserved in both cases. So if we graph energy versus time, if we graph the mechanical energy, it's just going to be a straight line. The potential energy is a maximum at maximum displacement, which generally happens at at our starting time, and then it's a 0 at equilibrium. And it turns out that it's a cosine squared graph is what this looks like, and so the potential energy kind of oscillates back and forth like this. And the whole time, because mechanical energy is conserved, that means it's trading off with kinetic energy, and the kinetic energy graph looks kind of like this. The key thing to remember is that as these systems oscillate, energy is being kind of passed back and forth between kinetic and potential. One last little bit, I just want to remind you, period, remember, is the time for one cycle. In this case, it would be the time for one oscillation. So for our mass spring, it starts out up above, goes to equilibrium, goes down to its maximum displacement below equilibrium, and here, and then here. Your period is from max to max or min to min. It's one full cycle. So it's down, back up. So max to max, or if I kept drawing, you go minimum to minimum. That would be the period. For pendulum, it's the same sort of idea. It's from, you start off over here, then you're at equilibrium, then you're back over here, then you're back at equilibrium, then you're back over here. It's swinging back and forth. And so we go from far left to far left. That's we go from the leftmost to the leftmost point, or rightmost to rightmost point. That is where you would measure the period of a pendulum. When we do a lab, you'll be measuring that time. It's also helpful to know, if you measure one period, then your reaction time is a larger fraction of the period than if you measure, say, 10 periods. So if you're doing a lab, it's a better idea to measure multiple periods and then divide. So say measure the time for 5 periods and then divide by 5 to find the period. That'll be more accurate than you trying to measure the time for a single period.